Hello, everybody. Today, for our working group 1 monthly research seminar, we have a guest speaker, Chen, as an assistant professor at Department of Computer Science at University of Bath. So, Xi, stage is yours.
Okay. Thank you, Maria. Good afternoon, everyone. Today, I'm going to introduce a niche problem when conducting an interdisciplinary statistical machine learning research. We called it an unrepresentative prior issue, which could be seen in a wide range of realistic implementation in various industrial sectors, including finance. It may happen when people are trying to set up prior distributions in mild to high dimensional problems when using Bayesian inference. And the Bayesian nested sampling was the probabilistic sampling method we used in lab research. So here I also use it as an example. Okay, so this talk will be split into 3 parts. First, I will very briefly introduce Bayesian inference and the nested sampling for those of you who are not familiar with this. And then I will introduce the Bayesian prior repartitioning, which is the method we proposed, and followed by some results and a discussion of the application domain. Okay, so Bayesian inference, that's a very simple one. I guess most of you should quite familiar with that. It's just we define a posterior. The formula is we have a posterior which is proportional to the product of the prior and likelihood, where prior is the knowledge, our knowledge before we conducting a specific task. And the likelihood is something that measure the distance between our model prediction and observed data. How familiar or how similar they are to each other. And the posterior is the refined version of the prior distribution in light of those observed data. So in recent years, Bayesian inference has been widely used in statistical machine learning research in many different kinds of problems. Because the domain investigated by all these problems are mostly continuous domain. So you have a continuous space, and some are with high dimension. So we often need to compute the integral in the Bayesian inference, which is in most cases computationally intractable. And so that in statistical machine learning, there are 2 streams of research directions developed in recent years to deal with this issue. The first one is called deterministic approximation. The most representative technique is the variational inference. And the other type is called stochastic approximation. These are rejection sampling, importance sampling, Markov-Chain Monte Carlo, and CMC, and also this nested sampling I'm going to introduce. So both these 2 streams are trying to help Bayesian inference to calculate the terms such as marginal likelihood to conduct the parameter estimation for those latent parameters of interest, and to do model selection using the marginal likelihood. Okay, so this is the nested sampling. Today I just try to keep mathematical expressions at a very minimum level, and mostly use the graphical aid to illustrate the algorithms and the methods. Nested sampling is one of the very interesting methods and also quite powerful, widely applied in astrophysics, in geoscience, in many heavy industrial problems, and also in finance for price prediction, I guess, and also yeah. So here is a just 2D example. If we define the latent space, we have as the set of theta, we have theta 1, and here's theta 2. Now we just randomly, or nested sampling, just randomly draw a few samples, random samples. Here we draw 5 samples in this 2D space. This is the unit 2D space. That means we have 0 to 1. It might be originally a range between, for example, 0 to 1000 in a continuous space, but in nested sampling, it should be firstly converted to a unit space. If it's more than 2 dimension, then it should be converted to a unit hypercube. Then we will be able to continue to do the nested sampling. And the reason for that we will explain later. So the prior distribution of drawing these random samples can be any. It can be uniform, can be Gaussian, or can be Cauchy or others. That doesn't matter. And suppose we also define the forward model that connecting this space theta with a forward model, for example, f plus some noise to some, well, observations, noisy observations z. So suppose we have this f defined, it may not perfectly emulate the or describe the real physical process, but we somehow have some kind of forward model that will help us to connecting this hidden latent parameter with the observations. Okay, once we got that, then we will be able to generate some gases. That's some Z1, Z2, and these are all Z's generated from theta 1, sorry, this notation, theta 2, things like that. These are not true, but some of them might be closer to the truth. And we have several gases. Then we can like acquire the real observations. We may only have one real observations or a sequence of real observations over time, depending on the problem. So in this case, we have one, if we have one real observations to make it simple, then we will be able to compare these 5 gases with the real observations and compute the likelihood L to see how likely they are. And that means we will have L3, L2, L1, and L4 and L5. So that's basically representing the weight of that particular drawn sample. So now we have the weight for each of the sample given these observations. These might be noisy, but it doesn't matter. We have we have incorporated the noise term in our model. Okay, then that's how we do nested sampling. We have the weights, then we know that we can compare the weights and have the lowest weight point. For example, it's this one. This one has the lowest weight point among these 5 points we drawn. Then we'll be able to constrain the unit prior space. Originally, that's a unit prior space, including this region and this region. But then we will be able to constrain it to the gray space bounded by this line and this line. And these 2 lines should have the same likelihood value to this point we draw, which is the lowest one. That means all the gray areas have the points in in the gray areas should have a likelihood higher than that point, this point, and these 2 regions. So in this example, it's quite simple, but in realistic problems, there is not always that perfect. So we might have 2 regions or 3 regions because there might be like low likelihood areas around these regions. That's possible. Okay. Then we discard that point with the lowest likelihood. Okay. And then we resample a new point, keep the total number of random samples as 5, and resample another point within this constraint gray region and compute its weight again. And once we got this new weight, we will be able to compare with all the 4 points, all the other 4 points, and find another lowest likelihood region point, and further constrain the prior space. Then we repeat this process to discard it again, constrain, resample a new point here, compute its weight, and constrain the prior space. Discard, resample, constrain, discard, resample. Continue doing this. Okay, so finally in this example, we found to fix the high peak region. That's the place we have the higher likelihood. And then this nested sampling algorithm is capable of finding the multi-mode regions, multi-mode high peak, high likelihood peak regions, using these kind of like constraining methods. So note that although this width is quite big here, but actually in practice, it might a very tiny bit string here, very tiny one. And we might repeat this process for thousands or 10,000 times. So we're actually cutting the prior state space into very tiny strings, lot of them. Okay, then if you check these two figures, you will see the darkness, the degree of darkness of are different. The darker region represent the higher likelihood region, and the lighter ones are the lower likelihood region. And because we have converted the original physical prior region into the unit region, then we'll be able to know that when it's white, the X here is the whole prior region, the prior space. So when at the very beginning, we have the space, prior space equals to 1 because it's a unit space. And then we constrain. And the extreme case here, the other side, should be 0. So for the prior space, each of that strings, the area in that strings, that would be the value between 0 and 1. And each of them, we will be able to know the likelihood because we have calculated. And the y-axis here is the likelihood we got. And in this way, nested sampling will be able to accumulate or integrate all those small strings at different likelihood region to compute the marginal likelihood or the Bayesian evidence. And these will be used for model selection or decision making. When well, for each of the model, we will be able to calculate this in calculate evidence in this way, and we compare which evidence is bigger. That means we have a higher marginal likelihood, and it's more likely to choose the model with a higher likelihood. Okay. These kinds of like methods has been applied and tested in many synthetic or real industrial problems. a very typical one is called egg box example. So on left hand side, it's like a ground truth model, simulated one. It's mimicking an egg box we used to contain the eggs, and that means we have lot of equivalent height, high peak region, and nested sampling will be able to find these high peak regions in this multi-mode problem. Okay, that's the end of the first part. Any questions here? Okay, let me continue then. So then let's move to the unrepresented prior issue. What's unrepresentative prior? So let's basically it's a phenomenon that our prior assumptions are far from the actual values, actual prior values, or actual latent space values given a data set. So this was the problem we discovered, or just, well, it exists for a long time. We came across that in a interdisciplinary research when developing a statistical machine learning method for a high dimensional inverse estimation problem in geoscience. And then these problem has been there for many years, and it make them like those in companies quite struggle cleaning the results produced by the statistical machine learning algorithms, because some of them, they might be wrong due to the incorrect prior stats by some of their engineers in a software platform. So as an illustration, let's first define the theta again as the latent variables, and we have a prior p theta. That's the Gaussian distribution with zero mean and standard deviation 4. So that's a flat dashed dot dashed blue curve here. We have zero mean. Okay, and in this standard case, we have a truth theta star equals to 5. That's here in a black line. And because we also define the Gaussian noise, so our likelihood is a Gaussian, you know, dashed green, difficult to see here, but that means our likelihood distribution will be around this one, and the theoretical posterior should be also very close to the likelihood one, and that's a normal case. So any of the sampling algorithms, rejection sampling or the nested sampling, MCMC, would all be able to give a perfect estimate. And this is the perfect estimate using a lot of samples. And we'll be able to finally find the posterior concentrating at the center of 5. Okay. Then, well, what's the problem here? It seems one page missing. Okay, it's again shown here. Okay, then what we just discussed, the theta star equals to 5. If theta star now equals to 30, that means we still have the prior knowledge here, but the truth is that our prior is incorrect. It might be still like not that far, but it cannot cover the region perfectly given by the data set. And that means our likelihood now will move to this bit, and theoretical posterior, the true theoretical posterior will be also very close to here. It will be shifting a little bit to the left, as you can see here. The red one will shifting a little bit to the left. That's because in theory, when we're computing the posterior is the product of a prior and the likelihood, and the product of two Gaussian, it will drag back a little bit from the green one to favor the prior one. Okay, that's maybe basically okay. So we call it a borderline case. Although there will be very, very few points can be randomly drawn from this far wing region of the prior, but we might still get some chance to find the points close to the likelihood, close to the data. Then once we find one of these points, it has a little bit higher weight. The sampling algorithm will be able to concentrate all their power to this region and find the correct one. So we will still be able to find the correct region and give a correct posterior in this case. But if we continue to move the truth from 30 to 40 or to 50 to 100 to 1000, because for example, in most of the problems, we don't really have a very tiny or small physical prior region. Then that means, for example, in most cases, we might have a theta belongs to 0 to plus infinity. Although infinity might be just too far, but it's the physical region in most kind of problems. Then moving these to 40 or 50 or beyond 50, we call it an extreme case. In most of these probabilistic sampling algorithms, it might be just fail. Or in MCMC, if you're familiar with the measurability testing algorithm, that might result in a very, very long burn-in period where MCMC was struggling and wandering around those plateau or very flat region and cannot find the correct region of interest in the state space. And in nested sampling, it might possibly result in an incorrect estimation of the posterior, for example, here. So for moving truths to 40, theoretical true posterior values should concentrate around here, around 39 point something. Okay, but in these sampling algorithms, because it's too far away, it can only return the furthest one explore, so to this value. So it's obviously incorrect, and that's the unrepresentative prior problem. That's basically okay for low dimensional problems, because we can just manually set those priors to a correct ones, or even it goes wrong, or taking a very, very long time cannot converge, we can still manually address that. But in a higher dimensional problems, because for each of the dimension, it might have a very different prior region, and most of them might be just continuous region, this problem will be quite serious. And also in real implementations, when there's a machine learning systems using Bayesian inference distributed in big companies, engineers from different parts of the world, they might just using these algorithms in their software online, and then they might need to set up their own prior region according to their needs in their specific task. So that's actually happened in a company we worked with, and then some of them they just cause problems. And the worst case is that it caused problems and they didn't notice that, because they still return some value, and looks can be correct. So that's the biggest problem. We didn't notice that, and it will cause further other problems then. Okay, so our solution to this is quite simple. We called it the Bayesian prior repartitioning, BPR. So introduce that, we first need to introduce some simple terms. We still keep the latent parameter, latent variable as the theta. We now have a p, theta is the posterior, and L is the likelihood, pi is the prior, and Z is the marginal likelihood or Bayesian evidence. So once we got that, the idea of a BPR is to try to maintain the posterior while changing the proportion of the likelihood and prior according to some rules. So we try to keep the detailed balance equation the same. This is the original one, and this tilde L and tilde pi are the newly defined effective, we call it modified of effective likelihood and prior. And this effective prior should be able to accommodate that unrepresentative prior issue. So here is the little bit more detail about tilde pi and tilde L. This is the normalized version where it comes from the original prior to a power of beta. This power coefficient beta is between 0 and 1. And that means if we want to keep the detailed balance equation, our tilde L can be determined. Okay, so then the problem becomes how we determine this beta. So intuitive interpretation is that the value beta, changing the value beta will make us shifting between the original prior when beta equals to 1. So we keep the original prior. That's the Gaussian distribution with illustrated here. Okay. If we keep beta equals to 0, that means we don't really have any knowledge of the prior, and that's just a flat uniform. Okay, so we are trying to find a proper prior distribution between these two, the Gaussian one and the very flat one, that can efficiently compute the posterior while avoid the unrepresentative prior issue. If we keep this prior too flat, too widen, then that means it's quite low efficiency. We also have a very broad region in the state space to search for. That's not good. So we need to find the correct one. And if manually we do that, for example, we set in the same example here, same example with the truth equals to 40, then we manually set this beta under this method equals to 0.6 in the left. This is the result. And the beta equals to 0.4. So we have a little bit flatter on the right, prior on the right. Then you will see that left-hand side one, you can start to doing the right thing. And then the algorithm is concentrating to the correct region. And it's doing a better job when we have a smaller theta, a smaller beta. And then the way to define or to find the correct beta is, well, originally we do it in a manual way, but that's not efficient. So then we continue to work on it and develop a joint distribution between theta and beta. So we actually, the idea is that adding the beta as the hyperparameter in the sampling algorithms. So we simultaneously estimate the latent variables theta and the hyperparameter beta. So that would solve this problem, well, automatically. Then that gives still a hands-off solution that can do posterior estimation and automatically avoid this unrepresentative prior problem. Here is another results using, well, the truth 5, and we have seen 5, 30, and we also illustrate 40, 50, all these. So in this triangle plot, this figure is for theta, this figure is for beta estimation, and this is the joint one. This is the joint one. You will see that with different extreme cases, you will have a different range of available beta. So that means for beta in this range, for example here, for 5, we don't really need beta because it's a standard case. So any beta would work. That means the beta can be just between 0 and 1. And for 10, it's okay. And for 30, although we have just shown that it struggle, the sampling algorithms are struggle, but they can still find it. But beta does suggest a better solution should be between below 0.4, 0.3, something like that. And that would give a very efficient exploration in the state space. And more extreme the case, a smaller beta we have. Okay. This is another 2D illustration of a similar extreme case. So manually fix the beta equals to 0.6. You'll find those sample points concentrating far from the truth. So here is the center of the truth, and this is the 68% confidence area of the truth. And if we continue lower the value of beta, you'll find the points of density concentrating to the correct region. Okay, we also tested some other results, including the correlated case. So rho here is the standard correlation coefficient of the 2D Gaussian case. So we have theta 1 and theta 2, and we have a correlation between them. This is the positive correlation and negative correlation are illustrated in this figure. And we set an extreme case here, which is also 40 and 40, far away from the correct one. The correct one is still the same as the example we introduced previously. Okay, so for different correlated case, these methods can still do a good job. As you can see, these beta case. Well, this is the theta 2 case, and theta 1 to the beta and theta 2 to the beta case, they are doing the expected drop. Beta will have different ranges, and they are a little bit different for theta 1 and theta 2. This is due to the probabilistic property. Okay. We then tried the multi-mode case. Two kinds of multi-mode case are tested. The first one is well, here is the prior. We have a prior, and we set up 4 different modes in a state space. It's a 4 modes case. Then we move the mode. This is symmetric case from the first point, first experiment the 4 modes are quite close to the prior. Then we move it far away from the prior, following the diagonal direction to see if the algorithm can cope this kind of a situation. And we also try the asymmetric case. We still have the prior here, but then put all the modes together and slowly moving it to a extreme case. And the results shows that this BPR method can do perfectly for the symmetric case, or a little bit in asymmetric is okay. But for this extremely asymmetric case, it can only find the flunt two modes. Well, if it's this extreme case, it can only find these two flunt modes, but fail to find the two modes behind it. That's because when we are expanding, automatically expanding that prior region using beta, when lowering a beta, when it finds this line, this region, we just like think that it's the correct modes are found, and just stop expanding to another further region. Okay, so that's one of the drawback when dealing with this extreme asymmetric case. And we also compare with this algorithm with the standard MCMC, the metropolis testing. Also the important sampling. You can, if you're interested in that, please refer to the paper, the details there. These methods with the BPR equipped, well, multi-nest is one of the implementation version of the nested sampling algorithm. So it did a better job regarding the root mean square error when using the same problems with the setup we just introduced in high dimensional problems. Well, when you say high dimensional here, it's comparing with the like dimension 1 to 5. So here we tested only to dimension 15. We have 15 dimensional cases. To further dimensionality, it still works okay, but computational cost itself is quite high for all the sampling algorithms, Monte Carlo, especially Monte Carlo sampling algorithms. So I didn't show it here. Okay, and this is the another results. Estimation of the beta over dimension 1, 3 to 10, and also the RMSE, root mean square error of the estimation for the latent variables, also in the 10 dimension case. We have tested examples up to 15 dimension, and in the real implementations, let's implement it in up to 10D problems. And here is one of the results we implemented. Well, not exactly that one, but very similar one. So I use it as an example. So here is a 8D continuous latent variable example. They have different prior ranges, all are quite wide. And then engineers will need to set the prior ranges by themselves for different tasks they have. They might have similar tasks, but not exactly the same. So they will need to set the prior range to make it faster, more efficient according to engineers' knowledge. So that's where the problem comes from. And using this kind of method, it reduced more than 50% of the computational cost when searching for a state space without like entering occurred prior unrepresentative prior problem. So this is the self-adapting prior that can avoid this kind of inaccurate posterior estimation, especially when there's a high volume of realizations need to be performed by different users at different time. Okay, So summary, this BPR can provide a robust and self-adapting and computationally efficient hands-off solution to this type of unrepresentative prior problem. And this has been tested in correlated multimode and non-Gaussian examples. I didn't show non-Gaussian examples here, but it's in the paper. We show the Laplace case and previously showed the Cauchy distribution case as well. So as long as there's an analytical expression of that prior distribution, then this BPR method could cope with it. And this can be applied to applications that requires setting up the prior distributions in higher dimensional space. This can be transferred to easily transferred to different industrial sectors, applications, including finance, as I said. Before the end, I'll just briefly introduce the center I belongs to. It's I'm a faculty member in a computer science department in University of Bath. Also belongs to the UKRI CDT in Accountable, Responsible, and Transparent AI. We call it Art AI. So it's a center in our department, well, in the university, across departments, doing a trustworthy and explainable interdisciplinary AI research supported by the UK Research and Innovations. We now have collaborations with a number of companies, including Rolls-Royce and DeepMind. So you're very welcome if you have any interesting research you would like to collaborate with us. And here's my own research interest other than the one I just shown. So I basically do a latent variable estimation and Bayesian decision making using the Monte Carlo methods, and also working on high dimensional surrogate model learning using Gaussian process and recurrent neural nets, and meta learning using a few like very limited training data, and ongoing finance and AI related work we're working on right now is to develop the Bayesian deep generative model for reliable high dimensional volatility matrix estimation in high frequency factor models. These high frequency factor models are extracted from the stock data. And so this dimension, each of the dimension, they are just time series. And each dimension represents one of the stock. So that can be more than 500, but we're now just testing the 250 ones. Okay, that's the end of my talk. Thanks, everyone. Any questions?
Thank you, Xi. Are there any questions?
Yeah, I have a small one.
Sure.
Can you show slide number 51 again?
Yep.
No, maybe it was 50, I'm sorry.
This one?
Yeah. So the beta coefficient is this exponent in this repartitioning, right?
Yep.
And so if beta is equal to 1, there is no repartitioning?
Yep, there's no repartitioning.
And if it's smaller than 1, then this is like taking a power of the Gaussian density. So let's say, for example, 0.5, then it's like taking the square root.
Yes, exactly.
But then, I mean, if I understand this correctly, then this would boil down to just using another standard deviation of the Gauss. So all these densities that we see there are just Gaussian density with a higher variance now. Is that not correct?
Yes. So we make it fat and flat. So just
Yes.
as like, yeah, like that. And this is just a wonderful illustration. It's not necessary to be, I mean, the original prior distribution is not necessary to be Gaussian. As I said, we have tested non-Gaussian cases, but Gaussian is a bit easier to illustrate.
Okay, thank you.
Yep. Thank you.
I have a question. How do you choose a beta, especially in high dimensional cases?
Yeah, as I said, it's the
optimal beta.
Optimal beta.
Yeah.
So that's a mutual process. It's like a expectation maximization. You mutually estimate theta and beta and trying to mutually find the best, because beta is now a hyperparameter as well. We simultaneously estimating it using the probabilistic sampling methods we chose. So that means, as I illustrated at the very beginning, beta will be one of the hyperparameters. We will always propose new random beta guess. Then we might guess at least iteration, we might guess beta to 0.53, 0.95, 0.13 or something like that. And then for each of the guess, we'll be able to generate the modified, the effective prior. And each of the effective prior will be used to generate the theta, to estimate the theta. And we will see which one works better, then assign a higher weight. For example, this might be, because this has a very low beta. In a very extreme case, this small beta value case will be assigned a higher weight. And then this beta might be just chosen in the next round to derive new other beta cases, other beta guesses. And we finally also come up with a best beta posterior distribution. If that makes sense.
Yeah. Okay, thank you.
Okay, thank you.
Are there any more questions? If not, then we can wrap up this research seminar. Thank you, Chen, again for a great talk.
Thank you, everyone. Thanks for attending.